Okay. Okay. All right. Now, first, I want to make a announcement, and it has to do with the second midterm exam. Okay. I would like to have given you more notice, but I can only give you one week notice. So the exam will be this day next week. All right. The usual, very similar in format, same length, same rules, open book, and I think the type of questions should be the same. I don't know whether Kevin plans to give you another sample test. If you have something in hand and you posted them already, all right, that's great. So we're talking about a second midterm exam, and it will be on April 17th, okay, 3:30 here in this room. Okay. Now, where do we? What's the coverage? I think the material up till last lecture, I would say, which is SOI. Of course, there's probably not that many quantitative questions we can ask about SOI, but there may be some qualitative questions. So, up till SOI, okay, up through SOI. What about the material that was already covered in the first midterm exam? We will cover them as well. It's very difficult to exclude that material because we actually have several important topics included in the first half of this semester. It has to do with the, say, velocity saturation effect on the IV, or the more accurate IV model, the short channel model. So there will still be some coverage, okay? But we'll try to put the majority of the questions in the second half, okay? Now, I want to explain a little bit why I'm giving you the midterm at this time, because I want you to have 2 weeks left unfettered by concerns and the needs to study for the examination, and devote that time to the term project or term paper, right? And I think I have mentioned this to you before. The last lecture or the last day of instruction for this course, of course, will be Thursday, will be the day that you make oral presentations of your term project, okay? You will still get, a little bit more time, depending how much more, depending on how much you would like. You help me decide after that oral presentation and before you turn in the written paper, right? Just a few more days, not that much. So basically, your term project will have to be finished in the first week of May. All right, not that much time left. So that's the idea here. Okay. Okay, I hope to see more of you in office hours from now on about your thoughts about the term paper topic. By all means, catch me after the lecture, after the discussion session, and talk about it. All right? Yes, Garth.
What about the homework that's also due on the 17th?
Oh, okay. Then we should make some adjustment, I imagine. I would think so, don't you think? All right. Now, that homework probably... how should we do that? Maybe is there still time to perhaps shorten that homework? Because if we delay it, I'm not sure it's helpful to you, because that homework presumably would be a good vehicle for you to study the material that will be covered in the exam anyway, yeah? Kevin, do you have some suggestion? Maybe we shorten that. Take away a question or two.
I propose not to make the deadline to next Thursday after the final.
All right.
I can post the answers first.
All right. Okay. All right. Sure. So your proposal is that we make the due date to, say, the 19th?
Yes.
but you will still, did you say post the answers before the exam day? That's your proposal? That's fine too. That's fine too. So it becomes a free homework then, right? All right. Okay. Is that good plan? All right. Okay. All right. Great. So let me get to the new topic today. Gee, this is not what I had in mind. Uh-oh. I missed quite a few pages of the note. That's all right. I need to borrow the book from maybe, I don't know, Kevin, can I borrow yours? Sorry. All right, thanks. All right, I won't review the SOI, except to say the last time we talked about SOI. Do you have any questions you want to ask about SOI? Okay, if not, we will move on to another topic. Now, what it is that there will be a large number of slides today, and if we cannot go through all of them, that's fine. We will not go through all of them. They are on this subject that I would call unusual devices, new devices, alternative devices, whatever you want to call that, all right? In other words, things that don't look that much like the standard MOS transistors, right? And you have seen standard transistors cross-section 100 times in this course. I know you're tired of it. So let's look at something novel. The background is that making the MOS transistors smaller and smaller has been the method of improving its performance and has been very successful. All right, obviously we'll try to do as much as of that as possible. But there's also the perception, and perhaps it's more than perception. Certain perception perhaps is also the reality that it's getting harder and harder to do that. All right. So we have to look for other ways to further get improvement. Now, for example, in order to get more current, what is the way to do it from scaling point of view? Well, the first thing is you're going to use thinner oxide. Is that right? Okay. Yes. You follow what I'm saying? But unfortunately, if you use thinner oxide, you also have to reduce the power supply voltage because of leakage current, which we haven't quite talked about, and maybe because reliability. Yeah. So you can think about what else can we do, things we haven't talked about in this course that we haven't considered variable. Well, one thing, for example, would be mobility. Is that right? Suppose you can use higher mobility material than silicon. Then it's wonderful. Is that right? Okay. And the fact is that in the research community, there has always been an effort to look at non-silicon material, usually compound material, 3,5,2,6 material, indium phosphide, for example. These are things. And this tends to be supported by the Defense Department for very specialized applications, and somehow just did not quite make it, all right? And even gallium arsenide remained a very small part of the electronics, although it's important still, nonetheless. And you have to agree that it is because silicon infrastructure is just too strong. It will be probably too expensive for the society to rebuild infrastructure to replace silicon. Right? And you just have to have so in other words, the barrier of entry is really too high. So alternative would be to somehow bring in some new material into the silicon technology in a way that's not very difficult, right? Using the standard manufacturing equipment, using basically the same CMOS process, hopefully, and CMOS design. The characteristics should look very much like the silicon CMOS, so that all the design, the cell, all the libraries can still be used, hopefully. And that would be nice. And turns out the one material that's most attractive from that point of view is trimmed silicon germanium film. In other words, what if we just grow a very thin layer of some material epitaxially over where we would have the channel, and the rest is still silicon. Suppose that's the case, right? And silicon germanium is also particularly attractive because it so happens that germanium chemically is very compatible with silicon, and some of you may even know the silicon germanium is already used in the bipolar technology in a big way today. All right, so that certainly shows you can put that into the silicon fab. But if we can, through doing that, get better MOS transistors, gee, if you can get the performance gain of one generation, that's certainly huge. You will be a hero, obviously, right? So what can we do with this silicon germanium? All right, so let me explain this a little bit. The diagram may be a little too complicated, but nonetheless, let's look at right-hand side. You don't have to worry about a well. This just means this can be done in a CMOS fashion easily. And I'll explain why some other ways are difficult to do. First, I'll show you this easy way of doing it. And I believe we did include this paper in the reader. This is by EE231 Yu, was published in the 2000 IEDM. Right? So you have isolation already done. Here we showed low cost. Of course, today no one would use low cost. It would be shallow trench. At a point, you would be normally in normal process would be just growing gate oxide, right? But instead of growing gate oxide, at that point you grow a epitaxial layer of very thin silicon. Now that actually is optional. It just so happens when you put the wafer into this epi reactor, it's better to first grow some silicon rather than growing silicon germanium. After growing silicon is a little easier, give you a clean surface, and then you grow silicon germanium. Is that right? Okay, so that's a minor consideration. And then you put down a thin layer of silicon germanium. It's 10 nanometer. Here we use the 76% silicon, 24% germanium. If you use higher percentage of germanium, the benefit will be greater, but also will be harder to grow the epi film. And this happens to be just about the concentration used in the silicon germanium bipolar transistor, by the way. All right, and all these things could change as we learn how to do this, of course. And so this silicon germanium film. Now, on top of the silicon germanium film, we grew a 40 angstrom of silicon cap. We actually don't want that. The only reason we want a silicon cap is because we know we cannot grow high-quality SiO2 on silicon germanium. That's a known fact. That is one problem with using silicon germanium, okay? And that certainly still require a lot of additional work. So the way we did it is just put very thin layer of silicon. We wouldn't have liked to even use thinner silicon. And then oxide can be grown on top of that. Do you see the idea? Okay, so after clean, after oxidation, hopefully not much silicon is left. All right, okay, but still we had more than what we like to have left there. Okay, and what else? And so oxide is on top of that. Of course, SiO2 is on top of the silicon cap, and then you put down your, let's say, polysilicon gate material, etch it, do spacer, implantation, exactly the same as an ordinary CMOS process. So the only difference is we add this selective epitaxial silicon germanium. The rest will be identical to CMOS process. All right, idea. Yes, Jane?
Do you use the thermal oxide or you use the LPCVD?
We use the thermal oxide.
Thermal oxide, so this, the top silicon cap is totally...
Unfortunately, not totally removed. We actually would have liked to have less left. It depends on how much silicon you put down to begin with and how much oxide you grow. As you know, today we don't need a lot of oxide, right? Say 20 angstrom of oxide, which means only 10 angstrom of silicon is consumed. So for high performance transistors, we're not going to consume a lot of silicon, all right? Okay. But indeed, our plan and in the future is to use even less silicon. And a lot of these, as you can see, is manufacturing thing, Right? If we're not familiar with how to do this, we'll take a more conservative approach, put on thicker silicon so that we know it's going to be to yield, so we'll have a paper to submit to IEDM. Right? But when there's more time, of course, we're going to try to use more aggressive technology. Okay, you see the general idea here? All right. The point is that we actually want silicon germanium. We don't really like that silicon, all right? But we have a little silicon there. Okay? All right. So what's the whole point? Well, the point is, at least the older way of doing things, is that it's known that silicon germanium has higher mu p, but unfortunately lower mu n. So for this reason, it really has not been taken seriously. A paper has been written 10 years ago already that you can make silicon germanium, CMOS silicon germanium, but you end up with more current in the PMOS and less current in NMOS. I don't like that. All right? Okay. Secondly, I want to point out what's meant by strained silicon germanium. Now, it turns out the mobility, the transport property has to do with the strain in the material. And when you grow epitaxial silicon germanium on silicon, because lattice constants of these two materials are not the same, the silicon germanium is under strain. All right? And the strained silicon germanium has this property. It's okay? So in the past, what people have done, for example, is they actually like to make PMOS in silicon germanium and make NMOS in silicon. All right, and it's very complicated how to do that. Or actually, they like to do NMOS in strained silicon. So what they do is, all right, we like this for PMOS. We just leave the PMOS alone. Now we grow even more silicon germanium on the NMOS side. If the silicon germanium becomes very thick, a few thousand angstrom thick, then the strain is relieved. All right? Okay? So now on top of that, people have grown a layer of silicon, and that becomes the material for N-channel transistor. Now that thin layer of silicon becomes strained because it's absolutely grown on unstrained silicon germanium. Do you see how this goes? Okay. So when you have done that, of course, process becomes very complicated. Now, what we have done here is we're proposing a new concept, is we accept the fact that the mobility is lower for NMOS. However, from theoretical study, we predicted we can get higher saturation velocity for both electrons and the holes. Because of the strain caused the band splitting, it changed the scattering such that we think the saturation velocity can be larger for both electrons and the holes. So here, I'll show you what we were able to do. Right? And indeed, we did see that both N-channel and P-channel FET ID set is quite improved. All right? First, let's look at the P-channel side. You notice the open symbol is silicon germanium, and the closed symbol is silicon. Is that right? Okay. And this silicon is silicon germanium gave us significantly improved ID set with the same VT. Now this is very significant. This is more than what you can get with one generation of technology scaling. All right, with this much of improvement. On the N-channel side, you notice when the VDS is low, silicon germanium yields lower current than silicon. This is the well-known problem. That is, the electron mobility is actually lower in silicon germanium. You see that? Right? And yet, when you go to saturation current, it becomes larger current. Now, this was not noticed before because people used to do all this experiment in long-channel transistors. Right? And this is done 10 years ago, so it has been examined and then abandoned. Right? Okay. So this just illustrate indeed the saturation velocity is better. Okay? And I want to point out, when we say L here, we're talking about effective channel length. It's not the gate length. So if gate length is 0.1 micron, the effective channel length will be much smaller than that, and we think the benefit for the current will be much larger. But anyway, so here just shows the saturation velocity improve for both electron and holes. As a result, if you look at the drive current for the PMOS, for any channel length, we see silicon germanium channel has higher current than silicon. Is that right? Yes? For N-channel transistors, we see silicon germanium transistor has lower current than silicon transistor at longer channel lengths and have better drive current at shorter channel lengths, and that difference is going to continue to increase, we believe. So theoretically, we think we may be able to get 40% improvement for both two transistors, and that will be very significant. Okay? Any questions? Yes?
I wonder if right now the channel is in the silicon germanium or silicon, but you still have the silicon.
Germanium.
But you still didn't consume all the silicon, top silicon.
That's right. So therefore, the performance is not as good as it can be. When we fully consume all the silicon, we think the performance will be even better. So right now, some of the electrons are still in silicon, some in silicon germanium. So this is, again, you have to why we have to study and know the detail about things like the quantum effect, where the electrons lie. Even if there was no silicon germanium, where are the electrons? Are they really all in the top 10 angstrom? Or where are the electrons? Do you remember the electron profile? Is that right? Okay. We can tolerate some silicon. That's all right, actually. We can still have most electrons in silicon germanium and still end up with high quality silicon dioxide. Again, these are the things people did not appreciate before. Right? Yes.
Well, I wondered for the ID set, it improved. So it's the distribution of the mobility.
It's due to the improvement of the saturation velocity. The mobility is actually lower in this transistor. Okay? And that is why, if you look at the IV curve, at lower voltage, actually silicon germanium sample give us lower ID than silicon sample. It's only at a higher voltage in the saturation current region that silicon germanium gives. Because here we're looking at the mobility. The slope is all determined by mobility, as you know. All right? Okay? All right. So you can imagine the optimization of such transistor can be a very interesting question, right? So, yes?
Maybe I missed a point, but I couldn't understand why in long channel MOSFETs the current is lower for silicon germanium.
Because the electron mobility is lower in silicon germanium than in silicon.
But it's also in saturation region, right? So, I mean,
What
the
is in
reset,
saturation region?
I mean, the drive current.
Maybe we'll look at this figure here. You're looking at VDS equal to what voltage is your question about?
No, I'm questioning about the long channel and the short channel.
Oh, you're talking about here, I'm sorry.
Yeah.
Talking about this curve here now.
Yeah.
Is that right?
Yeah.
Okay. So here the concept is that we're all looking at saturation region, we're looking at ID set. But the concept, as you know, is that for longer channel transistor, the so-called long channel transistor, mobility dominates, the velocity saturation effect is weak, right? Remember our model actually smoothly go from the long channel where it's all due to mobility, saturation velocity totally drops out of the equation, to the extreme case where it's all determined by saturation velocity. Mobility actually does not come in. Remember that? All right? Of course, real transistor is always in between. Is that right? Yeah? Okay. Yes.
But it's really confused is that with the mobility decreased, then you still have a big ID set. So what happened to it?
All right. Let me answer this question by reminding you, in this more accurate IV model, that's why I emphasize so much about these models. You know, it's not just pretty equations. I think they're really very interesting physics in it, and if you understand it, you can make good use of it. Remember, I had this discussion with you. I said, if you look at this equation and look at extreme case of L go to 0, remember I wrote down ID set turns out just equal to Cox Vg minus Vt times Vset and times W. I don't know if you remember this particular expression or not, right? And I introduced this by telling you, gee, isn't that surprising? This is totally independent of channel length. This may remind you that we have talked about this, right? But interpretation it makes a lot of sense, you know, and also it does not depend on mobility, by the way, Jim. That's why I'm answering your question this way, all right? You're asking why the mobility can be very low and yet saturation curve can be very high, all right? I'm trying to answer your question. You notice in this equation, mobility does not come in at all. And remember the way we interpret this equation? We said it makes a lot of sense. You know, current should always be equal to velocity times the charge, right? If this is the most charge you can have, that's the current you can have. That's the velocity you're going to have. Therefore, that's the current. This corresponds to the case of what? This corresponds to the case of Vd set equal to 0. All right? If Vd set is equal to 0, this is the charge density at the drain. Right? This charge density at the source and at the drain. Right? And multiplied by the saturation velocity is your current. Yes? So, you know, these equations does tell us a lot. And, you know, we can try to answer new questions always by going back to these concepts, these equations. They're not complicated equations. Yeah.
So you're saying that Vsat is higher in silicon germanium than in silicon?
That's exactly right. Right. So that's exactly what's believed. The saturation velocity improved. This interpretation is the motivation for this approach. Okay. All right. All right. So clearly, you know, depending on the technology in the future, it may be possible to grow epitaxial indium phosphide or something else on silicon substrate. So again, we can see things. There are ways to keep moving things up. And silicon, by the way, relatively speaking, is not a high mobility material. Actually, there are materials with mobility that are 10 to 100 times higher than silicon. That's amazing. It's an amazing fact. All right. Okay. All right. Okay. Any other questions? All right. Let's look at something else. Okay. You know, we have seen this before, but just because I have the slides, so I'll go through this with you. The smaller FET transistor needs a thinner gate oxide. All right. Why don't we just read through this? The conduction channel must be controlled by the gate, not by the drain. What I mean is that whether the channel conducts current or not has to be determined by what voltage we apply on the gate, not what voltage we apply on the drain, right? If it's determined by what we apply on the drain, we won't have a transistor, we'll have a resistor. It's maybe a nonlinear resistor, but it's a resistor, right? And at that point, we just don't have a transistor. So if there's any scaling limit, that must be a limit. When a transistor becomes a resistor, that must be the limit, right? Okay. So in order to avoid that, then the conduction channel must be controlled by the gate, not by the drain. In other words, this capacitance is much larger than that capacitance, right? And you'll have already heard me say this many times. As the channel gets smaller, the CD becomes larger. That's the problem. And therefore, we have to make CG larger also, meaning using thinner dielectric, right? The problem is that, you know, how thin can we go, right? We're already using very thin dielectric. But actually, the problem is even worse than that. Oops, what I'm talking about. All right, let's just stop there. All right, we may have missed one or two slides, but that's all right. Okay, but that's all right. That's all right. Okay. All right. So let's start with that. So as a result, we just have used thinner and thinner oxide. If we use thinner and thinner oxide, several problems occurs. One is the polydepletion becomes a significant part of the total effective dielectric thickness. Do you know what I'm talking about? All right. So therefore, what you might want to do is you might want to do metal gate. All right. Replace. So how can you deal with that? So one concept is replace the polysilicon with metal. Is that right? All right. The challenge here is if you want to use metal gate, you better find two different metals with two different work functions. because from the design of N-channel, P-channel transistor, you have seen that if we only have one work function, such as N plus doped polysilicon, we cannot get high performance P MOSFET, remember? And vice versa. So finding two metals with the right work function is already a challenge. And secondly, challenge is process-wise. How do you do that? How do you put two metals, one on the NMOS, one on the PMOS? And suppose you put metal A on both and then etch it away from one side. That etching may attack this side, the thin dielectric below it. Is that right? Is that right? That etching of the metal? One way to put is that you put metal over both NMOS and PMOS side, or P well and N well. Then you use a mask to protect this P well and etch away the metal from the N well, right? And then you put down metal B on both sides, and now you have metal B over N well, metal N on N well. By the way, work function is thresholdly determined by that first metal in contact with the oxide. On top of that, whatever metal is stacked won't make any difference, all right? But doing that way will involve etching metal away from a very thin dielectric. That's not very desirable, okay? Another possibility is you etch this oxide away at this point, somehow add new dielectric. But that will involve, subjecting that metal to some high temperature. So there are always difficulties involved, right? And again, that's what research is about, okay? So students here actually have give the first report of a successful dual metal gate CMOS process. But it's not very satisfactory right now. There's still a lot of room for research. So one research that students here are doing and already have some success is see if there's a way to put only one metal across both. Did you hear what I'm saying? All right? And then cover one half of cover the P well, let's say, with photoresist mask, and then implant into the metal on the other side, and see if implantation can change the work function. Now, surprising thing is that in one experiment, the implantation of nitrogen into moly did change work function by coincidence, exactly 1.1 volt. Ended with 4.05 EV and 5.1 EV, which is exactly the same work function as N plus poly and P plus poly. All right. The problem right now is that it's not reproducible, and we don't understand the mechanism. In fact, these two things go hand in hand. If we really understand mechanism, I think we can make it reproducible. So there's still research going on, right? A lot of other ideas you may think of how to do that dual poly for the metal. Okay? So I'm just giving you different ideas how to deal with each of these problems. All right? Okay. Another problem is going back to the previous slide. Actually, with your understanding of the device physics, you can easily see it's even worse than this. The reason is that even if we make the oxide very thin so that the surface is very well controlled by the gate, yes? What is to prevent current flowing, let's say, 100 angstrom below the surface? Right? This may or may not be what this is not what most people think about as punch-through. Most people think about punch-through as really deep punch-through. But here we're really just talking about, anywhere you have silicon, the potential barrier can be lowered by your drain. And if the drain cannot succeed in lowering the barrier right at the interface because the oxide is thin enough, it will lower the barrier somewhere 100 angstrom below it. And that's where you're going to get the most leakage. Is that right? So just by scaling the thin oxide, keep scaling thin oxide may not be able to allow us to shrink our channel length. Yes? And that's why we have to shrink the XD max. You have heard this many times before, right? But shrinking XD max is very difficult. All right? Okay? Probably more difficult than shrinking the oxide thickness to some extent. And for all these reasons, and the other problems let me point out. So one is the oxide thickness. Oxide thickness scaling is very difficult, right? And besides, even if you scale oxide very thin, I still have question whether we can stop the leakage current when the channel length is very small. There's also the concern about heavy doping. By the way, heavy doping has to do in the substrate has to do with XD max question, right? Yes, yes. There's the shallow junction problem, how to make junction very shallow. Right? And another thing is called dopant fluctuation. I don't have a lecture prepared on this, so let me just say it, dopant number fluctuation. Okay, what that means this. You know, threshold voltage depends on the doping concentration, you know that, right? Yes? All right? Okay. Now, when the channel is very small, not only the L is very small, W is very small, but also XD max is small. So the whole volume where you have charge, and that charge is what we have been calling Q depletion, and Q depletion determines VT. Is that right? Is that right? The whole volume that contains Q depletion is very small. Is that right? Yes? Put it another way, the number of dopant in that Q depletion is very small. Even though the doping density may go up, in fact, recently it's not even going up because we're doing retrograde dopants actually, right? But anyway, so dopant number fluctuation, which will lead to VT fluctuation or any other device property that depends on the number of dopant or doping density. Okay, that's considered a problem. People have already noticed some static RAM yield is limited by or affected by this in a measurable way. So the concern is in the future, how can we continue to scale? But this has to do with scaling with dopant number for the following reason. You probably know Central's theorem that says very basic concept in statistics is the sigma is proportional to square root or inversely proportional to square root of n being the number of the sample. Is that right? All right. So if I'll give you an example here. All right. Suppose I ask you to count the number of, air molecules in, one. I don't know what's good. Turns out this is fine. 1 cubic centimeter of air, all right? And you sample this 100 times, all right? You're going to find these 100 numbers are very close to each other. The reason is in 1 cubic centimeter, there's lots of gas molecules, okay? Oh, by the way, the density of gas molecule it's actually not that small. It's only about 0.1% of the solid or something like that. Okay, so it may surprise you. It's actually not that low density. But anyway, so you see very small sigma. You see what I'm saying? If you sample the air molecular density using 1 cubic centimeter of sample size, you're going to find that 100 samples give you 100 identical numbers essentially. Now, suppose I ask you to count the number of air molecule in 1 micron square of sample. If the average, let's say, is only 100, now do you believe me? If you count 100 of them, you may see 10% variation. See what I'm saying? Now if I ask you to sample even smaller volumes, you're going to get even larger variation. Is that right? So this is known as dopant number fluctuation. So there are several of these problems that have made people think that there's a limit to device scaling. In fact, in 1999, there was a well-publicized discussed paper from Intel in Science magazine that claims that scaling is going to be a problem. Specific list is 3 or 4 limitations. All right. And if you look at the roadmap, this is in 1998, and certainly, even 99. But this gloomy picture I'm speaking, I really should trace back to around maybe 97, certainly in the last few years, because of some of the things we'll review today, the picture is looking much better. The roadmap in 99 would say up to this 0.1 micron technology solutions are being pursued. And beyond that, there's no known solution. And in fact, the roadmap ends at this point. So very often is referred to as the end of the roadmap. So we would do things like, we're approaching the end of the roadmap and things like that, right? So beyond that, it's not a known territory, right? Not knowing what can be done. So that's the kind of concern or picture that has been hanging over industry for about 10 years, all right? The picture used to, So the question is, how can we beat some of this perceived limitation? All right. So let me show you some possible solutions. Earlier, I pointed out one that I felt most serious. Really, is how can we prevent how can we turn off the transistor? Oxide scaling is limited, and even with very thin oxide, we're still going to have a leakage that's 100 angstrom below the oxide. All right. So there are two solutions, I think, that can be done. And so in 1997, 3 professors here from Berkeley wrote a proposal to DARPA to propose to demonstrate 0.25 micron CMOS. That's beyond the roadmap, all right? So we proposed 2 structures. So I'll tell you, these are the 2 structures. One is called a double gate, all right? One is called ultra-thin body. In both cases, the important thing is to make the gate silicon film very thin, all right? Such that there's no silicon that's far from 1 or 2 of the gates. So why don't we just look at ultra-thin body first, all right? You have heard about SOI last hour. This is not the usual so-called fully depleted SOI. Now, when the film is thin, the silicon film will be fully depleted. But this goes much beyond that. You know, fully depleted SOI is perceived to have problems with the series resistance, for example, right? So people would not want to make this silicon film any thinner than barely becomes fully depleted, right? Okay, when it's thin, you have a problem with making contact, series resistance, silicide, it's all a problem. Here we're talking about different thing. We're going to support ultimate scaling, so we're going to make the silicon film only 50 angstrom thick, for example. You see that? So we call this ultra-thin body. So the whole point is that if there's no silicon more than 50 angstrom below the oxide, then the problem of not being had gate control is solved. You see what we're talking about? All right? And this does not have to involve heavy doping in the substrate, right? Okay? And this is not going to, this automatically in a way deal with the shallow junction requirement. See that? Right? So certainly there are things that can be done if you think out of the box, right? So consider the and again the doping fluctuation. So how do we deal with that? What if we don't rely on the doping concentration in the thin film to determine VT? In fact, we cannot, because the film is so thin. Unless we dope this at some unreasonable high concentration, there won't be sufficient Q depletion to make a difference on VT anyway. Do you see what I'm saying? We might as well take advantage of that, not dope it to that heavy doping. In fact, we don't even bother to dope it. Suppose we don't dope it, do we still have any dopant fluctuation problem? We won't, right? Is that right? So in that case, how do you adjust the threshold voltage? You rely on gate work function engineering, right? We're probably going to go to metal anyway, right? Probably going to use other material. Silicon germanium is what we use extensively in this experiment. By changing the germanium concentration, we can change the work function of the material. That's the easy way to use as gate material, right? In the long run, it's probably going to be metal. So adjusting the metal work function will always be very interesting and important. That will be the new line for research, clearly. All right? You see what I'm talking about? All right. The other benefits I don't think people fully realize is how much benefit this can give us in terms of mobility. People don't realize that. If you don't have a heavy doping, not because of the Coulombic scattering, although that's important too, but mainly because you minimize the vertical field. All right? Okay? The mobility could be, this will scare you as 50% or maybe even double. We really believe there's that potential. So there's a lot of things can be done to further. So this is our proposal. So this is what I mean by alternative device, novel device. All right. The other device actually is less novel in that people have been talking about this for 10 years. This we think is more novel. So we first proposed this ultra-thin body. This is less novel, actually, in that people have been talking about this for 10 years. That is, although not everyone realizes it's very important to make this body very thin, but we think we have to make this body very thin. People like this for several reasons. One reason they like is they say, gee, you get twice the current, you get 2 channels. All right, that's not bad. This is one advantage, although to some extent it's probably not that significant in that you also introduce twice the capacitance, of course. So all you save is really some real estate, and if you're really limited by the real estate of a transistor, yeah, this will probably be very significant. But if you're not limited by real estate of a transistor, as in some applications we are not. Interconnect, for example, is a very often limitation. Then perhaps having twice the current is not such a great deal. But of course, having twice the current is good. We're not going to knock that, right? We like the current. So a lot of people have been looking at this. The challenge, once you get twice the current, I want to emphasize the benefit is that if you use thin enough film, then you can actually prevent this drain-induced leakage, and therefore be able to shrink the device to 25 nanometer, maybe even beyond. Okay? All right, so that's why this. Now the problem with the double gate structure is that there has been no manufacturable way of making it. As I said, it has been known for 10 years. Lots of these were just computer simulation, and there were a few brave souls that tried to fabricate this, but nobody liked, I think it's fair to say that no one was happy with the way these things were fabricated. All right? So the challenge there is to come up with a way that's at least the most manufacturable up to now. And of course, we hope that one of you will think of even more manufacturable ways to make this. All right? Okay, I truly believe we haven't yet seen it. All right? All right. So the key is to use very thin silicon film, and in order to deal with the parasitic resistance, we have to somehow do something to reduce that resistance, such as by thickening the thickness, right, outside the sorting region, right? Takes some more doing, but we may have to do something like that. Okay. So let me first look at the ultra-thin body with you. What's the benefit in making the body very thin? All right? This shows simulation. Now, it will be more obvious, more dramatic in color. Without color, you kind of have to take my words for it. What we're doing here is we're showing you 3 simulation devices. All have 25 nanometer of gate length, 15 angstrom of oxide thickness. All right? They are in the off state, so VGS is 0, VDS is 0.7 volt. If we put 1 volt, it will be even more difficult, of course, even more dramatic, the difference. And what we are doing very simply is start with what most people will consider already a very thin silicon film, 100 angstrom. See what I'm saying? All right? Okay? In fact, most people doing SOI would start probably with 200 angstrom, 300 angstrom, thinking that's the thinnest they want to fuss with. All right? Okay? So here's 100 angstrom silicon film. There's 75 angstrom silicon film. There's 5 angstrom silicon film. All right? What does BOX mean? What's the meaning of BOX? Buried oxide. Very good. All right? So you know what that is, all right? Okay. Part of XOI substrate. Is that right? Okay. Here we're showing you the current density in this off-state current density, basically leakage current. And you have to take my words for it. This 10 to the 6 is what this one is. So you see the worst place for leakage is far away from the oxide, which is not surprising if you just think about what I just explained earlier, right? So don't think that the current always flow along the surface, right? It's not surprising. That it cannot flow because the oxide is preventing the barrier from being lowered, but nothing is preventing from being lowered here. Is that right? So how do you deal with it? How about just cut this part out? Yes, cut the part out, leakage reduced by orders of magnitude, but still the worst place is here, right? So cut out even more. Now this becomes dark because the scheme somehow, this shows up here, right? All right, okay. You see what I'm saying? All right. This just shows it dramatically, orders of magnitude, you reduce leakage current. Right? Think about, if you don't do this, how can you reduce leakage current by orders of magnitude? It's very difficult. You're going to raise VT by 0.2 volt. Right, 0.3 volt. Now, what's the impact of that on the performance when the power supply is only 0.7 volt, right? So that's why the leakage current is something we have to really deal with using clever device structure. So next, how do we make such a device? So Young-Kyo Choi demonstrated this device. We buy the SOI material. It comes with 1,000 angstrom SOI film thickness. So we reduce this oxide thickness, silicon thickness, by successively growing some oxide and etch it away, right? Measure how much silicon is left. It's still too thick. We just oxidize some more and measure how much is left. You see? So it would take a few iterations to get to the kind of thin thickness we want. Right? And again, this is not something we're happy with. So if you have some ideas how to make these thin silicon film other ways, those will be really breakthrough ideas. A lot of opportunities for inventive creativity here. Yes?
Is this oxidation of an SOI wafer?
That's right.
But I remember that the oxidation actually happens subsurface at the silicon oxygen interface.
Correct. I cannot give you the actual very good answer to that. Apparently, it has to do with the oxidation condition. I'm not familiar how to do this internal oxidation. If you just grow oxide the usual way, you can still use grow oxide on top of the SOI silicon film. So that's why we can make transistors. But apparently, there are certain conditions. If you find it, then it's going to enhance the growth of the oxide at SOI and minimize the oxidation near the surface, right? And part of some of this is probably proprietary. You can speculate. Maybe you even want a very thin some layer of nitride on the surface to prevent from oxidizing, or something like that. We don't really know what's involved. Okay. All right. Okay. But normally you can oxidize the SiOI wafers, no problem. Doing internal oxidation actually is tricky. Okay. But it's doable also. All right. Okay. Good. Thanks for that question. Really good question. Really tie them together now. So after we have reduced the oxide SOI film to that thin thickness, we actually first pattern that. That will be the isolation, and then put down the gate and spacer as usual. You see that? Yes? Next, what Yang-Kyu Choi did is he put down selective germanium deposition to grow this thicker source and drain to reduce the series resistance. All right? Now, normally people would do selective silicon deposition because that's actually a well-known process in the industry. But turns out in our lab, it's easier for us to do selective germanium deposition. It just so happens because of the equipment and expertise we have. All right. All right. So you see what you see here is that's the gate with the spacer, the very thin silicon film. Turns out in this case, SOI film is only 30 nanometer. Not that we really need that. In fact, the best performance did not come from 30 angstrom of a film, but just to illustrate using this TEM picture that he was able to make the silicon film as thin as 3 nanometer. All right? And this is the raised germanium source drain. See that? Okay? All right. And so here's some performance that he was able to get. This is not the best data, by the way. So every 2 months, he and Day One is working with Yang-Kyu has some better data. So this current keeps increasing. And so but this is from last year, some data here, okay? And for a gate length of 40 nanometer, and we're convinced, with such good low leakage current at 40 nanometer, if we can make them at 20 nanometer gate lengths, I think it can scale to that, all right? You can see that, right? There's no problem with any leakage evidence of drain-induced barrel lowering or any other leakage. Is that right? Okay. All right. And so, because of the processing capability limitation we have, we cannot really push this device to the smaller scale we want. So we also use some simulation to extend our experimental data. Once you have some experimental data, now you can calibrate simulator and have some confidence with simulator, right? If you don't have any experimental data, then it's, people don't want to believe your simulation. But once you have some simulation experimental data, people are willing to see what simulators say, how much more you can do. So when we simulate this, similar condition, 1.5 nanometer, 18 nanometer gate, and we can see works quite well. Depending on the silicon film thickness, you can get either a few close to, let's say, 80 nanometer per micron of leakage current, which actually is accepted by the roadmap now for high performance technology. If you use a thinner silicon film, you can see how dramatically it reduces the leakage current. See that? Right? So this is the way to beat the scaling problem through novel ideas of the structure transistor idea. And here from simulation, we can get 950 microamp per micron of current, and I-off can be very small, right? Okay. All right. And well, I will not go through the other slides. So any questions about this ultra-thin body device? Well, maybe there's one slide I will go through with you. So look at this VT dependence on silicon thickness and substrate doping. First, on the substrate doping concentration. Did you notice that over a wide range of doping concentration, the VT is very insensitive to the doping concentration? Right? Yes? But this is because if the silicon film is thin, you just don't have that many dopant, right? So this is how you beat the so-called dopant fluctuation. All right? Okay. Of course, this is a sword of two edges, double-edged sword. On one hand, you got rid of the dopant fluctuation problem, but we also brought on a new problem, is how are we going to adjust threshold voltage? Do you see what I'm talking about? All right? All right. So there are some novel concepts, and the student also presented a paper last year, IEDM, reviewing some of this concept, how to do that. But it's not easy, using metal or work function of the gate is just one idea. But what other ideas are there to do that? It's not easy. All right. The other one is that we also noticed VT now is, however, can be sensitive to body thickness, even though the doping concentration is not very large. And we think it has to do with quantum effect, actually. And this is something that Day Won and Yang-Q recently just finished modeling this using quantum mechanics. You see, when the silicon film is so thin, we're now really talking about quantum well. And as a result of quantum well, the energy state rises. If the energy state rises, the amount of bending required for the surface to be inverted will be different. And this will have an impact on VT. Right? So this is another problem when the film is thin, something we have to deal with in planning, in dealing with the process variation. Another idea, and this is done by a graduate student, Jacob Kaczorski. He just started working at IBM. And that is, instead of using raised source and drain, we just silicide this thin film directly with silicide. If you do this, the main problem, I will not go with the detail with you, the other alternative, the main problem is that now the interface between the silicide and the silicon is very small because it's just the thickness of the film, which is small. Which means the interface resistivity better be very small. Now, this may not be something that you have considered seriously, but anytime you put silicide or metal on silicon, if this is silicon, this is either metal or silicide, there's a finite resistance due to the presence of interface. As current flows through interface, there will be some voltage drop, and that's called interface resistance. All right? And the way to minimize interface resistance is to use a silicide silicon Schottky barrier that has very low barrier height. We believe has to be less than 0.2, 4.22 EV. So for PMOS, platinum is not too bad. For NMOS, is no good material. And Jacob's contributions that developed technology using erbium silicide that give the best result. But even then, we still don't think it's very good, and more work has to be done on that. All right? but many companies are very interested in this and want to continue to develop that. And of course, this kind of low barrier technology is going to be useful even for the regular contact, just the usual IV, usual IC technology. Let's say 0.1 micron technology, 0.07 micron technology. The contact hole is going to be very small, right? You have to start worrying about what kind of interface resistivity there is. So you're going to need a low barrier. Well, in fact, since I got that far, let me just finish this thought and tell you about it. Today, we use one kind of silicide to make ohmic contact of both N-channel contact to N plus and contact to P plus material. We use the same type of silicide. So in this case, we better choose a silicide whose barrier work function come up to the middle of the band gap silicon, so that for both P plus and N plus contact, for both electron and holes, we have half of the EG as the barrier. This is what I mean. You want to choose material whose work function come to middle of EC and EV. In such a way, for electron conduction, the barrier is half of EG. You see that? That's the barrier. For hole conduction, the barrier is also half of EG. Is that right? For hole conduction, that's that barrier, right? That's the best you can do, right? And turns out titanium silicide, cobalt silicide all happen to have about mid-gap of work function, all right? In the future, what we really want is we want to have this barrier for electrons, this low barrier for electrons, and that low barrier for holes, right? So this means we're going to need two different silicide for the ohmic contact, all right? So this is how, and this performance of CMOS will continue to evolve, because there are still things that engineers can do beyond what we seem to sometimes consider as limit today. Okay, all right. Now, back to double gate. I mentioned the challenge of a double gate is really how to make it. I'll give you one example how it's made, and I guess there are two examples how they are made, some examples, all right? Let's just see one example, how to make such a structure, all right? Okay, final structure is on the right-hand side. So let's see how this is done. This is done at Fujitsu. Okay, so what I do, I have to think through this before I talk to you about this, all right? Let's see, how do I do that? How was this done? Okay, since I have a dotted line, it must be starting from the top, all right? It's a little complicated, so bear with me. So we start, let's think this way, all right? Oh, yes, let's start with this way. Good, I remember it. I think I know how to do this now, all right? What you do is, you start with a silicon wafer, so don't look at all the dotted lines. Dotted lines were not there, all right? Dotted lines were not there, okay? If you look at that, then it will be easy for you to see it's just a silicon wafer, yes? You grow some gate oxide, yeah? Yes? That's the gate oxide, okay? If you grow the gate oxide, you put on polysilicon gate material and define the polysilicon gate. So this is the polysilicon gate, okay? Yes? Yeah? After that, you will deposit some CVD oxide. You do polishing to get a smooth, flat surface. Are you still with me? All right. After that, you bond it with another silicon wafer. Is it okay? After that, you start etching away the top silicon. Remember, the silicon is still here. There's no dotted lines yet, right? You start etching this away as if you're making SOI material using a wafer bonding technique. So after you etch this way and left with the thin silicon film, now, let's see, this part, until you have 200 angstrom silicon film left. All right? Now you have SOI now. So you grow gate oxide again on top, right? Put on polysilicon material, define to get this last dotted gate. Voila, you have your double gate device, right? But even then, your two gates are not self-aligned. You see that? So this is what I mean by there's no not being a good way of making this, even though everyone agrees it's a good structure, all right? So other ideas people have done is Toshiba has something called a surrounded gate MOSFET. You will etch a pillar in this or a short wall of silicon in the silicon substrate. All right? It's okay? And then either due to epitaxy or just implantation, you create this situation, N plus on top and here. You grow the gate oxide and you put down polysilicon spacer. Remember spacer idea? You can put down a material that only surrounds the side wall, right? So you make this polycrystalline silicon spacer. They are the gates. These are the gates now. Now do you see what you happen? You have a gate on one side, gate on the other side. So this is double gate, is that right? Yes? So if you can etch this silicon wall that's thin enough, then you get a kind of double gate I said we want, that it has to be thin, all right? Up until recently, people actually have not been stressing that. They just thought, gee, we're going to twice the current. This looks nice. But if you want the benefit of really scaling, right, then you have to really make this very thin. Okay? By the way, we think it has to be a fraction of the gate length, channel length, in order to make the gate coupling much stronger than the drain coupling. You see what I mean? In other words, this will be a realistic drawing. That is actually the gate to channel coupling using the middle of the silicon film as the channel has to be larger than the channel to drain coupling, right? This means the film thickness has to be thinner than the channel length. Can you visualize that? Right. Now, how much thinner? Of course, that's the kind of research we were doing, and our conclusions twice would be fine. The silicon film probably should be no thicker than half of the channel length. Okay. So this drawing would not do it, all right? But anyway, it has the potential of doing that. Okay? And the variation of that would be actually to make this a small cylinder, etch a small cylinder out of it. In fact, no matter if you use a mask that's a little square, after you do the lithography, you end up with a circle anyway. So you always can etch a small cylinder, right? And maybe you can further reduce the size of the cylinder by oxidizing. And those are the novel ideas, right? Try to do that. Okay? All right. And I will not review some other ideas to give you the reference. This came from Lucent Technology, 1999, IEDM or so. Okay? All right, so what we did, now go back to what we did. All right, let me tell you another example. Another example, this is the idea that I like the best in 1997, before that. 10 years ago, 1990, Hitachi has presented published a paper. It's called Delta. Delta because I think it emphasized the idea that you get very tall pillar, right? Very thin silicon film. And I'll explain the concept. All right. So let's start looking at how they do this. They start with a bulk silicon substrate. Use a mask to etch silicon into pieces of this thin and tall whorls. Okay, we call them fins in our work here. Little pieces of fins. Each fin will become one transistor. All right. Okay. After they have etched them into fins, what they do is then they surround the whole thing with nitride. And they do that by first, already put some nitride before etching, and then do spacer on the side to protect side wall. All right? And then they put this into oxidation furnace. Nitride prevents oxidation, so oxide will grow on these areas. After a while, this is all covered by oxide. In fact, oxide will touch each other from left and right. All right? You see what I'm saying? Next, they etch away the nitride. Now what they have is SOI. You see, silicon on insulator. Right? You see that? This oxide is created by oxidation. Do you follow? Any question? Kevin, you seem to be still thinking. No? Okay. So you first etch a silicon like that. This is what you have. This whole thing is just silicon. And then you try to do something to cover top by nitride and also cover the side by nitride. Then you send this whole thing into oxidation furnace. Oxide will start to grow like this. You see that? Oxide will grow like that. Yes? Yes? Until it looks like this. Of course, there's oxide here too. In fact, that probably will be more realistic picture. Why don't I just change to that? You know, oxide will also have grown on top or so, right? You probably visualize that, right? Probably something like that. And that's true. And actually, it's very interesting, the structure. I will not go into details. Something like that, maybe. I'm just schematically doing drawing something like that. All right? Just show oxide will also grow. Okay. All right. Does this help, Kevin? All right. Okay. So this is how they get that. And then to strip the nitride. Okay. So now it becomes starting point of making transistor. Before that is preparing the substrate, you may say. And grow the silicon dioxide as the gate dielectric. Why don't I just add this? All right. So this becomes SiO2. And this is the gate material. You see that? Okay? Next, of course, use the mass to define the gate. Right? So source and drain and the gate. Now you see the gate is on one side of the channel and on the other side of the channel. So this again can be a double gate device, right? Okay. Now, however, we felt this process complicated, and also again there the emphasis was still in trying to get a lot of current. So they made this very tall, like 1 micron tall, all right, and film thickness about 0.2 micron thick. And it's not thin enough to really have the benefit of short channel, but nonetheless, I think it's very good structure. So when the DARPA proposal was approved, I invited the author of this paper to come to Berkeley to visit for 1 year, and his name is Dai Hisamoto. So we worked together and developed a better structure. So this is what we proposed, and even this name should be changed. We later had a better name, a more interesting name. We called it FinFET, so why don't we just call this FinFET? For a while, we actually called this folded channel. Let's call this FinFET, all right? Kevin, I'm using red pen on your notes. I hope it's okay. Kevin, I use red pen on your notes a few places. I hope it's okay, all right? So the red is, you know, is to make some change, right? So, okay. Otherwise, I'll use black, okay? So FinFET, what it is our goal is to make a simple double gate structure. So this is what we decided, all right? So what we're going to do, well, let's just do this. First, we're going to make the whole thing on SOI, we feel, all right? Just make it on SOI, okay? And so we simply go etch this thing on SOI. And secondly, we decided we're going to etch this thing that's very thin so that we're going to emphasize the scaling. And also, we're going to make the thing very thin. In fact, we decided to make it only 500 angstrom in height. This makes the etching simpler, make it more manufacturable. Of course, with better etching process, more selectivity, things like that, we do expect if companies use this, they're going to maybe use 1,000 or maybe even 2,000 angstrom tall thing. But our whole point is that one does not need to be greedy about height of thing. You can make the thing so the manufacturing becomes almost planar. So we kind of consider it quasi-planar, you see that, right? You know what I mean? If this thing is thin enough, it's almost like planar, right? And your other film is even thicker than that, right? Topography, all these. All right. So I will not go into the detail, but basic idea, schematically at least, would be look like that. Although in the particular reference that I cited here, actually the structure is not like that. It's different, but the gist is for this. All right, and this structure recently has been fabricated by another student, that's Nick Linder. This other structure was easier to do, so we did that first, and it has other benefits that we'll not get into, but this is the one that's easy to understand. So you just have a thing, that's a silicon, is this thing, and we have kind of a gate going over that, right? And the gate automatically self-align, you see, between in front and end. Right? And by making this on SOI, by making the thin height very thin, not very tall, we made this we call this a manufacturable double gate transistor. All right. Now, I'll just show you a few. Well, I will not get the detail now. Short in time. Why don't I just get into the results? All right, the electrical results. So the electrical results, so a few pages down, electrical results, all right? Here is a FinFET with 45 nanometer gate. It's physical gate, not the electrical channel lengths. And you see how good this short channel effect is, and very little G-induced barrier lowering, right? But we're even more proud of the fact that the ID set, right? This p-channel transistor, now you notice the n-channel transistor did not yield in that lot. As I said recently, another student did make a different process, FinFET, and made n-channel transistor, also very good results. This p-channel transistor, you notice the current is 820 microamp per micron. Let's remember this is n-channel transistor, p-channel transistors with 25 angstrom of oxide thickness. Tox is equal to 25 angstrom. At 1.2 volt, you get 820 microamp per micron. It's extremely impressive, all right? Reason is because this factor of 2 idea, right? Double gate, you have 2 gates, you have 12 2. But even if you divide it by 2, just still very close to the best transistor ever made. In fact, it is better than anyone can make with the kind of thickness that we used. And this is because the benefit of mobility due to the vertical field effect, the universal mobility kind of model that I think really has not been given enough attention, how important it is to affect the performance of the transistor, all right? So we're very proud that, in fact, this is the only double gate transistor that actually got not just factor of 2, even equal to the current as the state-of-art single-gate transistor. The reason is that when double-gate transistor is so difficult to make, you just cannot end up with a good results, right? So not only we got better than single-gate number and just about factor of 2 larger than the state-of-art single-gate. We're very proud of that. And in principle, it can actually be even more than factor of 2. I'll show you later if I have the time. And let me just show you one slide. There will 2 more than the end, maybe. One is that if you look at in the same study, there's another device that's 18 nanometer gate device, and actually the off-state characteristics still met the RTS requirement. So this is the world record in the gate length. And also the previous slide showed world record in the transistor performance. So new structure certainly holds a lot of promise. So status is that many companies are now known to be working on the structures. AMD and IBM have recently both submitted papers. So we'll look forward to seeing what results they got. And so we actually have some dream that this will become the mainstream device someday for, but if you really ask me, chances are there are even better structures, better devices to be invented. So keep trying, all right? Okay, any questions about today's lecture? Really talking about how to go beyond the perceived limitation of device scaling. Any questions? Okay, if not, then let's take 10 minutes break, and we'll come back and continue this. All right?